Okay, so based on the previous video, we already know how to set up the Linux environment and the Cadence environment, right? To run the simulation in Spectre. We have done a simulation to find the GM and out of a transistor. So our goal here is to design a common source amplifier, and eventually we tape it out and then do the measurement, right? So in those basic classes, we always just look at a common source amplifier like this, right? We have a transistor, we apply a small signal V in, and then this we have RD, and then this is our out, V out, and then we say the gain, right? A equal to V0 divided by V1 equal to negative GM RD parallel R out, right? And that's why last time we tried to find the GM and R out. Now, however, this does not have the DC biasing. I have told you many times we need the DC bias to set up the stage, to make the transistor into saturation, to get the correct GM and the correct R out, right? And we have learned how to bias it, right? One of the scheme is like this. We add a voltage divider. Maybe this is R1, R2, right? And this is the input to the transistor. You see everything is the same, except now I have this biasing branch R1 and R2, right? This is to set up a certain voltage because this is VD, right? So what is the voltage at this point? Is R2 divided by R1 plus R2 times VD, right? And then we have a coupling cap, and then we put the V in. So with this, then we'll be able to apply a small signal on top of this large signal, right? On this, on top of this voltage, right? And as a result, we can have a input like this, right? And then we get the output. Now the problem for this is that we need to put one more resistor. This R1 and R2 need to be large so that it won't cause a big potential divider effect when because we still have a RS here, which is the source resistance that you cannot see, right? But we don't want to go to detail, right? Another way is that maybe we can just bias it with a constant gate voltage. For example, you may say, hey, how about this? How about we do this, right? We bias it with RD, and then like this, and then I have an external pin that I just put a certain voltage, for example, 2.3 volts, right? And this is VDD, and then this is V out, this is V in. This is also okay, but then I need an extra pin, right? So later you will see the pin is going to occupy a large area in our design, because we need to have a large pad. And so I don't want to waste the pin. I save the area for other purpose. Later you will see the layouts of the whole chip, right? So that's why here we use the self-biasing. We have this RD here, and then we add the RG, right? And then we have the cap, and we in, and then we out. And this is the circuit we are trying to design here. So we need to do the capacitance right, do the RG right, otherwise they will be fit through, right? And then also the RD, and that's it, right? So we already done the design, right? And this is the design that we eventually come up with, right? So you see here we have a capacitor, right? We have a capacitor, we have the resistor, and this is VDD connected to ground. Particularly for the 65 nanometer technology, how do you make the capacitor and the resistor? It is not a simple thing, because some of them are actually a well resistor, so you actually need to bias the well to the ground also. So why is that? For example, right? If you look at a resistor, it might be just a line of, let me try to draw it in 3D. right? A line of this stripe, and maybe let's say this is N plus, right? N doped silicon. But this is located in a well, right? In a substrate, I should say that it is in a substrate, right? And this might be p-type, right? So you are required to also bias this one to ground, so that your resistor will behave as what is expected. Otherwise, the depletion between the p-n junction is going to change during the operation. So that's why we are going to bias the p at the ground, and then you have two terminals to this resistor, right? So this one act as like a resistor, okay? And similarly for the capacitor, it's a metal insulator, metal MIM, we call it MIM cap. The design rule also asks us to bias it, okay? So we'll look at this. So now I go back to the original terminal. I want to create a new cell, right? I say File, New, and then Cell View. Again, it attached my lab test library. This time I'm going to call it a CSM, Common Source Amplifier, right? But I'm going to look at this. Be careful. I'm going to do schematic, so it will be here schematic, right? And I use schematic maybe XL to open it. I say okay, right? Then you have this window, maximize it, right? So now what I'm going to do is to copy that structure. I'm going to do it step by step. I also forgot exactly what was the design, the number. So I would like to use this as a guidance, and you can work with me. Okay, so the first thing I'm going to add is the transistor. Again, where do I get it? I get it from the GPDK45, right? And then I look for the NMOS LVT. This is the one that we have studied before. Now, look at this. W is 10, L is 500 nano. So I need to change it. I know that because we already done the design. We know the GM give us the value we want. So this is a very wide transistor. 500 nanometer. Length is 500. Yes, finger width is 10 micron, right? Then the total width, we only have one finger, right? If you remember, we talked about the finger structure in the class at the beginning, right? In order to reduce the gate resistance. Here we only have one finger. We don't care that much, and we just put it here, right? You move. Don't hide anything. You can hide actually. Just move your cursor to the canvas and left click, right? Then I have the transistor. Again, how do I zoom out? I press F. Then you zoom. Zoom in. I press F. I see the full screen. I press Shift Z. Should be Control Shift Z, right? It's difficult to see. Let me just press this demagnifying button, okay? Sometimes my laptop doesn't work well. Okay, now then what do I need? I need to add a resistor, okay? So now I'm going to add a resistor. Go to here. This time I still need to use the 45 nanometer, right? I'm not using a ideal or just an ideal one, right? I need to do something that is from the PDK, right? So this resistor is called what? Resist NS poly. So it actually is using a poly as the resistor. What I just told you is a well resistor, but in this case we choose the poly, which is the gate, right? So this is resist NSPP poly underscore 2, okay? They have different properties, but we chose this because we found that it has the right value, okay? Now, then I need to go down. There's something very important we need to follow. Otherwise, you might run into the some error. So this what we need to copy from. This is R1. Okay, let me make sure this is R1, right? Which one is R1? R1 is the gate to drain, right? Gate to drain resistor, right? Okay, so this is R1. So, okay. Guess I put in the wrong place. So I'm going to push this and then move it, press M. Then I will move it to, you press M and then click on it and then move your mouse, okay? Move your mouse. I'm going to put it, let's say here. Okay, and full screen, right? So now I'm going to follow what we did earlier. Click on this and type Q, right? This is the capacitor. What I'm looking for is R1, this one. Right, the first thing you see the well node, you need to ground it, right? Instead of VDD, GND, right? And then everything is the same, but I'm going to make the width very narrow, right? So look at this, the resistance was 3 kilo ohm. Now I make it narrow, 200 nano meter, right? And then I make it really long, 100 micron. Then I will get a high resistance. Yeah, but it's not the same. I still need to make the segment equal to 19. Okay, then I get 4.175 ohm, right? So what is the meaning of this segment? Is that it's going to have a serpentine structure. We will see that when we are doing the layout. Okay, so with this, we just say okay. Then I should have the right resistance. Okay. Now, then the second thing is, again, I will need to add another resistor. I'm going to do add. And this time, what do I want to add? It's the same resistor, right? It's still the same. Let me check to make sure. It is still the same type of resistor, which is out resistor NSP poly. Okay, so I'm going to do the same thing. Resistor NSP poly underscore 2, right? So I will put it on the higher level, so I make it smaller, zoom out, and I put it here. Okay, and I type escape and then click on this, type Q, right? So I can start editing the property of the resistor. So again, I need to look at the cheat sheet, and this time what I'm going to put is, again, I need to ground it, GND, exclamation mark. Segment is 1. This is a relatively small resistor, right? 500 nano ampere. Micro, and then 50 micrometer. So 500 nanometer and then 50 micrometer. And this gives me 65 kilo ohm. So we have done calculation and simulation before. We know that we want 65 kilo ohm for this to work. Okay, and then I just say okay. Now I then need to add the I save it just to be safe, right? And then now I'm going to add a MIM cap, right? So let me just make sure the model name. The MIM cap is G45CMIM, right? So I'm going to add and look for the, right? You can use browser also, right? We were using browser, but here I just directly use this cell. It is what is the model? MIC should be a CMIM. Okay, I actually should not have this. It's wrong. I should look remove the keyword and then I should, where's my C capacitor? If somehow it doesn't work well, so I just come back to here. Okay, see if that will work. Okay, here. Actually, it was there, but I did not see it. I think it should be this one, MIM cap. Okay, I'm not sure, but Let's see that if that is right, right? So I can do, I think I can do control. No, it doesn't work. Oh. Anyway, I will just put it first, put it here, right? And this is right, the name is right. So I click on this, I want to rotate it. I think I can do edit and then rotate. Okay, I forgot the shortcut. I learned it, okay, and then you click on the one that you want to rotate, right? And then I'm going to click on this and then move it to here, right? And same for this one, I click on this and then I think I should just click on rotate. I'm not very good at this. Rotate and then click on this guy and then it will rotate, right? And then I just click the left mouse button, hold it, and then I can move it around. Okay, so I move it to here. I'm going to move the cap to here, right? So I need to now click on the cap and type Q so that I have the right value. And this is the value that I need to put. The goal is this: I'm going to have a width of 5.6 micron and then length of also 5.6 micron, but the multiplier is 600. Okay, so we have 600 copies. So we get a very huge capacitor, 37 femtofarad. Okay, then I just say okay. So I'm done with this, right? So I can do shift zoom, shift Z, right? Or I just do this, click this magnifying glass to make it smaller. So let me go back to see what else I need to put. I think I only need to put the voltage source, right? And also the power supply. So I'm going to link them. This one link to here. This is the drain. This one link to here. This is the drain. This one link to here, right? This is the gate. This one link to here. This is the gate. I need to put two voltage source, and voltage source again, it should come from the analog library because the PDK itself does not have that thing, right? So I look for VDC. Okay, I put one here, and then I put one here. Okay. Okay, I have an extra. Just click on this and then press D. No, I just press D and then click on this. No, I'm wrong. How do I press delete? No, D. Okay, and then I also need to add the ground signal. Okay, and then I connect that. This one come to here, this one come to here. Again, the body and the source are connected, and then they are connected to ground. Right, and here again, you click on one terminal and then click on another terminal, then they are connected. Here, I also need to connect them, right? Now, and then I click on this check and save. Now, there's one warning. What did I do wrong? Yes, right? So I forgot to connect this one to ground, right? There is one terminal of this capacitor I need to connect to ground. So I click on this. It's a little bit lousy, but let me do this, right? So that I make sure it is connected to ground. So it's wrapping around. Check and save again. Now everything is okay. Okay, now we want to have, again, if anything, just type escape, right? Change this to 1 volt because this is our design. The gate voltage is at 1 volt, right? That is one thing. And then how do we perform a check and save again? AC simulation to find the gain, right? So how do we do that? So what we will do is this, right? We again go to, I think we will go to here, type Q, and then apply an AC signal. Now the DC signal is no longer important because we have the capacitor. Now when we say apply AC signal equal to 1 volt, it doesn't mean that we really apply 1 volt. It is just that as a unit because it's 1. Remember, it is a linearized circuit when we were doing the AC simulation, as we discussed in the class, right? We have the DC bias, then we have them in the saturation, then we convert it into the AC signal model, which is a linearized circuit. So it will be linearized even you put 1 volt or 10 volt, which is not realistic. We don't put 10 volt AC, but however, the gain will be the same. So we can put 1 volt and then measure the output, that will be the gain. If you put 0.1 volt, then the output will be 10 times less, but the gain is still the same. So remember, AC magnitude doesn't mean that you really put 1 volt to it, okay? In reality, okay? It's assumed it is just the magnitude we input by assuming it is linearized, so the gain and everything are still the same, okay? So I say okay, and then I will save it, and then what do? We go to launch ADEGXL, like what we did last time, creates a new view, and then say okay, and then we add a new test, right? Not here, should be here, right? We click on add test, like last time. We want to do CSM, right? So I say okay, and click on this, right? So what we want to do is an AC simulation, and we sweep the frequency, right? Let me take a look what we want to sweep. We want to sweep from 1 hertz to 100 megahertz, okay? So I'm going to say 1 to 1E8, and yeah, start and stop, and then just say okay, and then let's run it, right? Once it's done, you just click this button or click here, run it, and then on the lower left you see it is running, and then it say it is pending. Now you have more simulation now. Last time was just the DC bias. Now you're running an AC simulation, right? So let's wait, and it is done. It has 6 warning. Again, I don't care here. Now I have some problem. I forgot to say what I want to observe. Okay, so I need to go back one more time. So I double click this one, and then I need to say here. Do you see this? This note. Don't know which one is which. It doesn't prop up. I think it is this one, right? You can choose what you want to observe. You can do from design. You just click from design. Then we want to look at the output at this point, right? So you just click at this point, okay? And then let's go back. Oh, it doesn't work. Let me try one more time. From design. And I think maybe I need to click here instead. Yeah, and then this is called net free. You can see that it is here, right? And then you just say okay, and then go back to the ADEXL, right? And click on it again. It should be at the bottom tab, right? Look at the bottom of your screen, and then let's run it one more time. Okay, click on it. Okay. Okay, and somehow it does not prop by default. Does not save. Let me click on this one more time. There was some glitch, and I need to run one more time. Run the simulation one more time. Okay. Oh, actually, it is saved already. Okay, so this is the gain, right? You see the output is in volt, but our input is in 1 volt, right? So this is the gain already by its magnitude. When you go to very full frequency, the gain is very small. But then the gain picks up when you reach about 100 kilohertz to about 7.7, and then it drop off. Do you know why? Yeah, think about that, right? We have learned about the biasing before. For the high frequency part, it's just because the transistor capacitor start to playing a role. That's why you have a pole, and then you start dropping off, right? And then, but for low frequency, why this one it is not has a low gain, right? We can look at the circuit. We'll go to on top CS amplifier. This is because at low frequency, you have a large potential drop across this capacitor. Okay, remember this one is tied to the drain, so this is not infinity. As a result, when you have a large potential drop across this one, you actually get smaller voltage applied to the gate. So that's why the overall gain is smaller. So in order to increase the gain at low frequency, I need to increase the size of my capacitor. But then later you see the layout is going to be very large, right? So my design is okay if I'm only interested in the frequency of, let's say, 100, sorry, I said it wrong before also, 100 kilohertz to 1 megahertz, then it is okay. If you're interested in amplifying this region, then it means you need to have a very large capacitor or a very large RG or R0, and that your layout area will increase a lot. Okay, so we are done with the schematic and also the simulation. Now the next step, right, what we need to do is to do the layout. But before that, let's go back to here one more time. You see, the length is 500 nanometer. W is 10 micron. Can you go back to simulate to find out the GM and R out? And then based on the theory of common source amplifier, see if you get the correct gain at the mid-band, that is this region. And remember that when it is at mid-band, we can assume if we have a well-designed transistor, this one we assume is infinity, and we short this one and see if you get it to be GM R0 parallel RD.